In this final pipe flow video, we are going to talk about how to compute minor head losses. So let's review real quick. Recall that total head loss is the sum of all our major head loss and the sum of all our minor head loss. So if we have a lot of different lengths of pipes, we sum up all their individual head lengths for each individual length of pipe. If we have multiple sources of minor head loss, we're going to add those up as well. So recall that major head loss is our friction factor times the ratio of the length to the diameter of the pipe times the mean velocity squared divided by 2 times the acceleration of gravity, and that's equation 9.23. And if you are confused on how to use that equation, go back and look at the major head loss video. Today we're going to talk about minor head loss. So what is that minor head loss that I alluded to? Well, they're losses due to geometric variations in the pipe. So it could be bends, it could be expansion or contraction going from a big pipe to a little pipe, or a little pipe to a big pipe. Any components, elbows, T's, these are elbows, I'll show you a T in a minute, valves, those are going to cause some type of losses, some reduction in pressure. So minor head loss is determined experimentally. It occurs when flow deviates from that of fully developed flow. So here's a diagram where we have an entrance loss on the left-hand side, and you can see where my normally laminar flow would be separated from the walls here, and that's going to cause a loss. Or around this long radius bend, you can see I have separation of flow as well. So I'm slightly deviating from fully developed. It'll reattach and eventually become fully developed again, but I'm going to incur some losses because of that. This is more significant in short, complex pipe networks. I mentioned this in the major head loss video. If I have a long segment of pipe, major head loss is going to be the dominating factor. But if I have a short set of pipes with a lot of different of these connections or bends or valves, minor head loss may actually be the dominant factor. So how do we compute minor head loss? Well, minor head loss is equation 9.28 in your textbook, and it's just K sub L, which is our loss coefficient, times the mean velocity squared divided by 2 times the acceleration due to gravity. And this was determined experimentally. So just to put in your notes, KL is the loss coefficient, and we get loss coefficients for different additions to pipe networks from figure 9.6. I'm going to go through each of those with you. The key thing to note is our loss coefficient depends on geometry and is completely independent of our internal Reynolds number. So let's keep that equation here on the bottom, and let's go through the table in the book. So for entrance and exit flow loss coefficients, this is figure 9.6 in your book. This is the top half of it. Let's observe some things. So on the left-hand side, these are entrance flow loss coefficients. So you can see if I have something re-entrant, like a pipe sticking into a container, I have a higher loss coefficient of 0.08 because I'm going to get some recirculation, some losses here on the sides. Whereas if I make it sharp edge, it reduces it. If I start to round it or put fillets on there, I continue to reduce it. And if I taper it like a funnel, and you know this by using funnels, I have much less loss. The loss coefficient is very, very small. Now compare that to exit flow loss coefficient. Something important on this exit flow loss coefficient is that it has to be flowing into a full container. If it's not flowing into a container, into another liquid, into itself, it's just like a free jet, so I don't have any loss coefficient. But if I'm flowing into a fluid, then I'll have loss coefficients. And notice that it doesn't matter whether it's reentrant, sharp-edged, slightly rounded, or well-rounded, they're all a loss coefficient of 1 because it doesn't matter. They're already outside the pipe. I'm not going to worry about that recirculation, but I will have to push against the fluid that's already in here, so I'm going to get some losses from that. And again, that's how we find these loss coefficients K sub L. So let's keep that on. Let's look at the rest of the figure 9.6. For sudden contractions, expansion, loss coefficients. So let's kind of orient ourselves. For sudden contractions, so I'm going big pipe to little pipe. I have some kind of connection there. I'm going to take a ratio of the area, the cross-section area of the small pipe over the cross-section area of the big pipe. And where the area difference is 0, the ratio is 0, meaning I have a large difference, that becomes the same loss coefficient as if I had entrance flow. If it's 1, meaning the areas are the same, meaning there is no contraction, obviously the loss coefficient is 0. And so you can look at the same thing for sudden expansion. I'm going from a small pipe to a big pipe in this case. It's a ratio of the small pipe to the big pipe. So make sure you keep track of which is A1, which is A2 in those ratios and the associated loss coefficients. So for pipe component loss coefficient, I have a huge list here. And this is not all-encompassing, this is not all-inclusive, but this is what you're going to need for this course. And I'm going to show you some pictures because it's very easy to look at this diagram and say, okay, it says long radius in my book or in the problem, let me just plug this number in, but I want to add some realism to this. So we're going to go over some of these things. So we got elbows, 180-degree return bends, T's, unions, and then valves. Let's go over a couple of those. So here's a bunch of component examples. In fact, every kind of combination is contained herein. So we have a 90-degree long radius bend. It's a 90-degree long radius versus an immediate 90-degree bend. You can see that the loss coefficient will be less for a long radius because it's a more gradual change as opposed to an immediate 90-degree bend. Here we have threaded fittings as opposed to a flanged fitting. And flanged fittings are used in high pressure applications because I can distribute some of that normal force, that normal stress in the pipe to the tensile stress or the normal stress in these bolts. So these are used in heavy, thick pipe, high pressure applications. You use a flange as opposed to a thread, so you don't have those threads fail and blow out, or as opposed to using something that's welded or soldered, depending on the application. This would be a solder connection where I would weld or solder this thing. But also, it's easier for maintenance to take these off as opposed to unthreading or having to cut a pipe. This is a 180-degree return bend, and this is a couple or a union, a threaded couple or union, and this is a T-fitting, so flow would go in and it would split. Let's look at a couple types of valves, and it'll kind of make sense if you understand how the valves work, why they have different loss coefficients. So this is a globe valve, and this is a common valve that you would see, let's say, coming out of your house, if you're trying to get water out of the side of your house, out of the faucet outside your house. The loss coefficient is 10. It's a pretty big number, and you can see it's because I twist the knurled knob at the top, adjust the stem, the screw, and I'm going to raise this disc up and down. But you can see the flow has to change direction. The more directional changes you have in the flow, the more areas of recirculation, the more separation, the more losses you are going to have. Compare this to, say, an angle valve, where the flow is coming up from the bottom and going to the right. It works the same way, where the disc is lowering and closing to change my mass flow rate, but the loss coefficient is much less because I'm not changing the direction twice, I'm just turning it 90 degrees. Compare that to a gate valve, and a gate valve depends on how open or closed, I should say, the gate valve is. So a gate valve is literally just going to move this gate up and down as I rotate the stem. And you can see if I'm a quarter way full, my loss coefficients are quarter way down, I should say, blocking the flow. It's 0.26 as opposed to halfway down, which is 2.1. If I'm 3/4 of the way, this gate's closed, it's 17. And for those of you taking ME350 or MC311, this acts exactly like the sluice gate in your open channel lab. The flow is just going left to right. What's causing all those losses is some of it, which is the threading, and the other was how much the gate's being closed. This is a swing check valve, and the loss coefficient's pretty small too. It's still noticeable, but the flow is going in left to right in this three-dimensional drawing, and so the flow is having some loss because it has to push this hinge open, this hinged flapper valve open. But the point of this is it would prevent backflow. So if the flow started going the other way, it would close this valve, so my loss coefficient would be infinity. It would completely stop the flow. Think of it for your electrical engineers like a diode. It's only going to allow current in one direction. It's only going to cause or allow flow in one direction. So this is a ball valve usually used in more robust applications, and you saw these when we went through the steam power plant. And you can set multiple settings. You can have fully open, half open, fully closed. That's what this drawing I pulled off the internet has, where the flow is going straight through the ball valve, and I can vary that. In their book, you have coefficients for open, 1/3 open, and 2/3 open. And you can see that when it's fully open, this loss coefficient is very, very, very small, 0.05. It's as if it's barely even there, and that's the advantage of a ball valve, is that there's almost no loss when it's fully open. And as you can see, as I close it, that increases significantly to 2/3, produce a lot of drag trying to go around a curved surface into the remaining opening. So let's sum it up. Minor head loss. Your equation is 9.28. It's your loss coefficient times the mean velocity squared divided by 2 times the acceleration due to gravity. Now, there's another way to express this that's in your book and could be asked on an exam or a problem set. I can also write my minor head loss as a friction factor, which you learned about in major head loss, times the equivalent length divided by the diameter times the mean velocity head. This is equation 9.29. Well, this looks just like your major head loss equation, and it really is. What you're saying is this bend or this coupling or this valve adds the equivalent amount of head loss as some major head loss of a pipe of some equivalent length. And you compute that using this relationship where the equivalent length is the loss coefficient times the diameter divided by the friction factor for the material you're looking at. Okay, that completes this video.